In this example, I'm going to teach you one of the most important transformations that can be done to a quadratic function, that of completing the square. Let's take a random quadratic function. In this case, I've selected 3x squared minus 5x plus 1, and let's complete the square. To complete the square means to carry out a sequence of algebraically equivalent transformations. Let me show you what exact sequence. The first thing we do when we complete the square is we identify the leading coefficient. In this case, that is the number 3. Leading, that means that that's the coefficient in front of the highest power of x. So we take the leading coefficient, the number 3, and we factor it out from the quadratic and from the linear term. So we forget about the constant term, so this guy is unchanged, but these two terms, 3x squared and 5x, they are transformed by factoring out the 3. Now, of course, when you factor out 3 from x squared, you're left with 3 and x squared. But what happens with the number 5? What happens with the number 5 when we factor out 3 from it? Well, we get a question mark. So what should I fill in place of the question mark? I'm sure you guessed it correctly. Under the question mark, there must be 5/3. Why is that? Well, when I uncover the parentheses, here I'll be getting, so when I distribute here the parentheses, I'll be getting 3x squared from the first two. But from these two, I'd be getting 3 times 5/3 x, the 3 is going to cancel, and I'll be left with 5x. Now you're going to say, well, how did I know to put 5/3 there? What I did was simply I took, say the number 5 is the number A, number 3 is the number B, and what you see here is A over B. So you always take the coefficient in front of x, you always take the coefficient in front of x squared, and you divide the two numbers, and you get 5/3. The next step in completing the square is to ensure that we have the number 2. So we need to make sure that we have the number 2 in front of the linear term. Okay, so now the number 2 is not present in front of the linear term 5/3 x. So what do? Well, we multiply by 2 and immediately we divide by 2 to restore the equality. So once again, in the next step, we always multiply by 2 and we divide by 2. So that's the next step. Okay, what's the next step? Before we proceed with the next step, let's just simplify a little bit. 2 times 3, that is 6. Now, here comes the real magic, the most crucial element of completing the square. We need to add a certain quantity and subtract a certain quantity so as to make the expression that you see here into a perfect square. So, I need to select the question mark so that this becomes a perfect square. So can I select the expression that you see here so as to get a perfect square? Okay, I'm sure you must have guessed it by now. If I were to select the number 5, 6 squares and I were to add and subtract that number, of course I wouldn't change the expression that I'm seeing here because I've added and subtracted the same number, but at the same time I would be able to generate a perfect square here. But why is that a perfect square? Well, let's think about it for a while. What happens when you take the expression a plus b and you square it? What's the formula for a plus b squared? Well, I'm sure you remember that is a squared plus 2 times ab plus b squared. So now, if instead of a we had the letter x, if instead of the letter a we had the letter x, then the letter x would correspond, so x squared would correspond to a squared. Well, the 2 would correspond to the 2 here. Remember, I told you that we need to manufacture a 2 in front of the linear term. That's always so that we can make this trick here work with the quadratic. And the letter x here would correspond to a. And what would b then? Well, this number 5, 6 would have to be b, so as to make the expression that we see here match the pattern a plus b squared equals a squared plus 2 times ab plus b squared. Well, if b is 5, 6, then b squared naturally becomes 5, 6 squared. Okay, so we have to add 5, 6 squared and subtract 5, 6 squared in order to complete the square. Now, once again, you can see that the number 5, 6 is going to be shown in 3 places in our computations. Here, here, and here. So we have to see the same number on multiple positions in our computations. Okay, now as we mentioned, this here is a perfect square. And that square is, I'm sure you remembered what we just did. The square that you're going to see is going to be x minus 5, 6, the whole thing squared. So we're having x minus 5, 6, the whole thing squared. Okay, now what happens when we take 5, 6 and square it? Well, 5 squared is 25 and 6 squared is 36, so there we get 25 36ths. Okay? We are essentially done with completing the square, or at least with the difficult part of it, but when we complete the square, perhaps the very final step we do is to distribute. So to take the number 3 and multiply it out by this guy and by that guy. So let's do the last step. So once again, the bulk of our work is done, but let's do a little more. So let me multiply 3 out by the square. And of course, when you take 3 and multiply it by 25 36, right? So when we distribute here, we'd be getting 3 times 25 36. But 36 is divisible by 3, so we can cancel out to 12, right? Because 3 times 12 is 36. So we get here 12. And we're almost done, except that this can be simplified. So 1 minus 25 12ths, that can be simplified. What's that equal to? 1 minus 25 12ths. Well, I'm sure you guessed it correctly. That would be minus 13 12ths. And that completes the transformation of completing the square.